Okay, hello and welcome to the second of these videos. I hope you're finding them useful. We're still looking at outcome 3, kinematics, and today we're going to look at the second part of the task, which is the 4-bar linkage. This one's slightly more complex than the previous one, but still fairly straightforward if you follow the right procedure. You will need a few more tools though. For this one you will need a compass, you'll need a protractor, you'll need a calculator, and you'll need a ruler. Everything we're going to do is draw to scale. So we're going to analyse a 4-bar linkage system. So if we look, this is the system I want to analyse. You'll note it's drawn. We have an angle of 60 degrees. We have 120 RPM going anti-clockwise. AB is 40 millimeters, CD is 80 millimeters, AD is 150 millimeters, and BC is 150 millimeters. So you'll immediately tell by these two dimensions and these two lines that this system is not drawn to scale. In order to do this analysis, we need a scale drawing. So we have to see how we draw to scale. So the first thing we do is we're going to start, and what we should see is that section AB of our system is 40 millimeters long at 60 degrees. Please forgive this. The software seems to be corrupting it as I share it. So this is AB. This is 40 millimeters long, and it's been measured in the software before I drew it. This is going to be rotating around point A, so that's why I've traced a dotted circle, just so we can see where the tip is going to go, and that is going to be moving with a constant angular velocity of 120 RPM. Now, you might think the next one would be to draw section BC, but we actually draw CD next for a reason. And you don't draw CD. I've drawn it in here to show where stuff comes from, but I'm going to explain the process we go through. Okay, so section CD is 150 millimeters away from section A. We know that measurement. We also know this member is 80 millimeters long, so that's drawn to scale there just to show us, because what we're going to get is this is the radius of another circle of travel. Now the problem is, while we know where this point is in space because we've got this angle, we don't know where this one is, so it could be anywhere along this line of travel, although it's highly unlikely it's going to be down here with the nature of the movement of the piece. So what we're going to do is, this is where you get your pairs of compasses, and you set your compass to 80 millimeters, 8 centimeters, put the point on point D, and sketch this arc here, a bit like where you were doing your technical drawing with Cliff. Okay, so we're going to set a point along that line. Now we go and look at section BC. Okay, and we do exactly the same for BC. We set 150 mil for our compass, set the point on point B, and draw this arc here. Okay, so what you're seeing here is these two lines currently don't join where they should be joining, because I've just drawn them in to show you the radius. What you're going to have on your page is hopefully that. Okay, and this point here is where point C is. Okay, so if we finish this off, we now draw a line up to here and a line from D to here to complete our space diagram. Okay, and if you measure these, you'll find that everything works out to scale. Okay, so from this space diagram, we've now got what those lengths are, and we've got what the angles are, which is the important bit for our velocity diagram. Okay, so that's the space diagram we're going to do, and we're going to take this into another piece of software now, where I'm going to show you what we do with the next bit. Okay, so what we're going to do is build the velocity diagram. Just bear with me while I find it. Yeah, application. I'm trying to find it. Sorry, that one. No. Application. I'm sorry, I don't seem able to find that one. No. Okay, I don't seem able to find that window right now, so it's definitely there. So what I'm going to do, I'm going to drag this to this side, and I'm going to share the screen with you instead. So I'm going to share screen too. Right, so you should now be seeing the same diagram, and I've got a compass, a protractor, and a rule. So you can see my rule, we are pretty much to scale, that is 15 mils. I drag this around, see that's 40 mil. If I measure that member there, 150, and I assume you'll believe me on the last one. So what we're going to do now, we need to draw our velocity diagram. So a velocity diagram involves tangential velocity, everything acting at right angles to the member. So if we look at AB, its tangential velocity is going to be acting along this plane here. So I'm just going to draw a line in there. Make sure our line is black. And I'm going to draw it in there. I'm going to make it slightly thinner so we can see, in fact, do that line, draw a new line in, slightly thinner so we can see what we're doing. And that should, we're being correct, also be at 30 degrees. So you see how my angle is slightly out. It's not too horrendous that I can't fix it. So you'll draw it in. As long as we're near enough, we'll get somewhere close enough. So we've got our tangential velocity, and that velocity is v with respect to a. Okay, I'm going to do exactly the same thing now for the other two. So we're going to measure 90 degrees to this line here. That was a pretty good guess. Not far off. Get that centered. That's 90 degrees. So we put in another line. We make it white. Nice, red, sorry. And again, it's going to put it in as straight as we can. Currently, I'm just drawing these vectors in on my diagram faintly, making sure I then don't change the angle. Okay, and finally in green, we're going to look at this one. Now, you might be wondering why we're not bothering about D. And D doesn't matter for this example because D is along the same velocity plane. It's on the same fixed point as A. So A and D are the same points in space, which means although we've got a quadrilateral here, our velocity diagram will end up being a triangle, and then we can solve it. So if I just move this out of the way, you can see I've got 1, 2, 3 velocity vectors. Okay. Now what we need to do is measure what angles these are so we can draw our velocity diagram to scale. So we're going to start here, find our horizontal point, and we know that this is 30 degrees. Okay, so our first line on our diagram will be drawn to be 30 degrees. And this is where we're coming here. It will be this line here. Apologies for that. You all know what that is. And if we get my protractor on this screen as well, I'm going to shrink this protractor down a little bit so it's not taking up too much of the screen. And 30 degrees. Okay, so now what we need to be doing is working out on this what's the length of that velocity is. This is where we're going to come in here. Okay, we're going to do some calculations on the whiteboard. Okay, so we know that we are spinning at 120 RPM. So the angular velocity is 120 RPM times 2 pi divided by 60. That gives us the angular velocity of AB. And that is equal to 12.7 rad per second. Okay, but that isn't the velocity we want. We want the tangential velocity of point B with respect to point A. So the velocity of point B with respect to A is equal to the length of the member, 0.04 meters, times by the angular velocity, 12.7 rads per second. So the velocity of B with respect to A is equal to 0.5 meters per second. Right, and that we know is acting 30 degrees, and it will be pointing in an anti-clockwise direction because the thing is turning anti-clockwise. Okay. So there's our first calculation. If we go back to our screen, okay, here you can see that I have my BB with respect to A, 0.5 meters per second. Okay. So, just bear with me 1 second. Oh no, I can't do that to that screen. This is going to be fun. So that is 0.5 meters. Oh dear, no, ignore that, forget I did that. So that is 0.5 meters per second. We need to draw that to scale. So I've picked a scale where 0.5 meters per second is going to be 10 centimeters, as you can see from that rule on that page. Okay, so that's the first line I've drawn on here. Okay, so I'm going to go back to the previous slide. Okay, now we're going to look at our green line, our V with C with respect to D, and we need to work out what angle that makes with the horizontal. Okay, which, looking at this, is 20 degrees. Okay, we're at 20 degrees to the horizontal. Okay, so what I'm going to come do now on my velocity diagram, I don't need a calculation for this, I don't know what it is, but at 20 degrees here, centered on point C, see I'm slightly down on that one, so we'll just change that there. I'm just going to draw a long line. So what I would suggest you do is, it's actually easier to draw it again, I think. There we go, I've got that to 20 degrees now. Draw your line so that it passes through 20, mark your 20 degrees point, okay, then mark 160 degrees or 20 degrees down from the same point. Then you've got 2 points that you can draw your straight line through, because as you can see there, that is by no means through that line. The problem with this is when you move one part of it, the other bit doesn't necessarily follow. That is about as close as I'm going to get, I think. Okay, so we're just going to draw that across into space. Finally, we go back to our space diagram and we look at this angle. Now I can do it from here. You can obviously read that, but as you can see, that was it. That was not what I wanted to do. View, zoom, no. So clearly I can't see from there, but fortunately I know that this point is exactly the same point. Okay, so I'm going to draw up and down 76 degrees from there. Okay, so come on to my next page. Okay, 76 degrees from the end of here. Okay, which is 76 degrees. It's going to be easier to draw a new line. Okay, take a new line, make it red, slightly thinner, 76 degrees. Okay, now that is the tricky bit done. Final thing we do, okay, to get the velocity, bear in mind that this point A and point D. This point C, and this is point B. If we want the absolute velocity of point C, we need the tangential velocity with respect to A or D. The easiest way to get that is to take our rule from our scale drawing. We take our rule, we measure the length of that line. Your drawing may be different. Mine is reading 9.7 centimeters. Okay, so we're going to go back. We're going to share the whiteboard again. Okay, so what we've got is that V of C with respect to B, sorry, V of C with respect to, sorry, V of C with respect to A is equal to 9.7 centimeters. Our scale was 1 centimeter equals 0.05 meters per second, and that's because 0.5 meters per second equaled 10 centimeters. So if we know that, then we know that the velocity of C with respect to A, which is the fixed point in space we're measuring things to, so is its absolute velocity of C, is equal to 9.7 times 0.05, which if we type that into the calculator gives us an answer of 0.485 meters per second. So that would answer the absolute velocity of C. In essence, that number would give us the answer to part A of your task using the numbers you have. Okay. Part B of your task is to find the angular velocity of members C, D. Well, as it's angular velocity, it's the same all the way around. So we now know the point at the end, and we know that CD is 0.08 meters long. So the angular velocity of CD is equal to 0.485 meters per second divided by 0.08 meters, which gives us an angular velocity of let's just do 0.485 divided by 0.08, 6.06 radians per second, and that gives you the answer to part B. So that should be 2 tasks you can now complete on this assessment. I hope we're getting a bit more slick with it. I hope you're understanding things better. I'm getting more software to help me, and I should see you next week with the next video. Thank you for listening.